Welcome everybody to Conversations on Critical Operations. I'm Nick D'Orazio. We're talking again today with Dr. J. Patrick Kennedy. He's the founder and CEO of OSIsoft. Hello, Pat.
Hello there, Nick.
And we want to go through some rules that you came up with, hard-learned lessons over the years. Let's just get into them. Let's start with it. You've got one rule. It's called, "It's the architecture, stupid." Can you explain?
Yes, that's an interesting rule. There was an article maybe 20 years ago called The Rise of the Stupid Network. It was by a guy named David Eisenberg, and it actually got him to leave AT&T. He was an AT&T engineer. And what he determined is that instead of working at the edge, AT&T was trying to do everything centrally. They wanted to do your switching. They wanted to do your voicemail. They wanted to do your call waiting. They wanted to do all of that stuff. And of course, because they were such a behemoth, it was unbelievably slow. So things that they had known about for years on how to accomplish weren't even possible to be done in the decade that he worked there. And so what he did, he formulated the idea that really it's a stupid network that you want. You want it to be blazingly fast. You want it to be ultra reliable, but you want it to stay out of your business. You want it to do one thing. You want it to move data from here to here and do it the way it should do it, but then let you work at the edge and find out what to do about it. So he wrote The Rise of the Stupid Network. And as part of that, I had a discussion with him sometime after that. And we talked a little bit about the complexity of the telephone system. And if you think about it, if you look at your handset, if you look at your smartphone, it's a radio. If I'm sitting in the same room, your radio can attach to my radio. But how does it really do it? It basically, my radio contacts a central NOC, which then establishes where your radio is, and it sends it over to your NOC, which sends the message back down to you saying that there's a call that should take place. And they do it all for billing purposes. But at the end of the day, it's the two radios that could have talked to each other would have been literally 5 orders of magnitude faster, and it would have worked much better. And that's really where I came up with the idea. It's the architecture. We have to look at the architecture of these things, because if we embark upon the wrong architecture, no matter how clever we are, we'll never get it to work.
Okay, fair enough. Are we doing anything within our software that takes advantage of that?
We look a lot at architecture. Architecture, like I mentioned, that the processing needs to be done at the edge in the stupid telephone network. The word edge didn't even exist at the time, because they were saying, okay, you can't get onto our lines because of safety reasons or whatever reason. But of course they could. We all in those days, we had our alligator clips that we'd clip on the phone lines so we could take our 9600 baud modem and dial back into the head office. But yes, we had to look at the architecture. Today, we have the same issues. So if you're doing things like, if you're trying to use advanced sensors like cameras or synchronous phasers or vibration analyzers or whatever, there's a huge amount of processing that goes on before that data is usable, and it's processing that's done every time. And so the whole architecture of the application is changing to allow us to be able to increase the scale of these things by doing more and more processing at the edge and just sending the result back to the central system. This is also requiring that we really address the problem of how people maintain these things, because how did that calculation get out there in the first place? How does it similar to other calculations of the same kind? So yes, we look a lot at the architecture and how that's going to be able to satisfy not what we're doing just today, but what we plan to do over time as the systems allow it.
Okay, great. So another one of the rules, if you ever hear the words computers are fast or memory is cheap, fire all the people, cancel the project, start over. Explain, please.
Well, I don't really fire anybody, but what I was trying to say there is that I have, over the 50 years I've been doing this, I've seen many places where basically the capacity of the system is supposed to overcome maybe inefficiencies in the software. So people may not want to do things like compressive data management. And so they'll say, oh, computers are fast and memory's so cheap, I can store everything. But what they don't realize is that even though computers and memory are accelerating according to Moore's law, which is doubling every 18 months, and that is true and sometimes even greater than that, people's expectations are increasing at a faster rate. So if I tell you, oh yes, there's a store in the future, you're going to walk in, pick everything up you want, put it in your cart, walk out, all the billing will be done. You never have to go to a cash register. You'll say, oh, that's really modern. Of course, they're doing it today. But if I'd even said it 5 years ago, you would have said, oh yeah, it's coming, because your expectations are that you'll be able to do things like that in the future. So I'm just saying, be very cautious if you ever hear those words, because people are underestimating the growth in the user demand for that system.
Okay, cool. Another rule. If you're in the middle of the forest and have a finite amount of food, the only strategy that's guaranteed to fail is to sit down and eat the food. Can you explain?
Yes. In fact, there's another way to say that, and that is that companies that invest where they're weak desire to be average. But the key is that if you have a position and you want to find the truth or find the future or get things done, there's some risk involved. And you don't just say, well, I can't take any risk, I'm going to sit down and eat my food. In a way, that's the most risky strategy at all, because you'll run out of food and there'll be nothing to do. So what I'm really saying is that you have to push forward, but you have to push forward in a conservative and a reasonable way of doing it. I remember talking to an engineering contractor once. I told him that when they build these refineries and whatever, they're too conservative. They're not ready to try, my fantastic advanced control or whatever it was I wanted to sell them at the time. And he looked right at me and he said, you think about that the next time you fly in an airplane or go across a bridge. Do you really want the people designing that airplane to be taking risks to find out what's most modern? And that really changes your viewpoint.
Okay. So now there's a whole mess of things that you've talked about scope over the years, and these rules reflect that. So can you describe in general what you mean by this, or what your first take on scope?
Well, the rule there is that your data set you need to solve a problem is set by the problem. So if you set out to do a problem and solve a problem, you don't just bring in the data that's available. You don't just go to a database or a data lake or an instrument system or whatever and say, now I have the data, I'm going to go solve the problem. You look at the problem you're trying to solve and go get the data that solves it, and that's set by physics. We were doing a system, actually our first system ever, in a refinery in Hawaii, and I asked them about these sensors that were out in the field that were not brought into the instrument system, so we couldn't see them. They would be thermometers on the bottom of columns. They might be pressure gauges on the top of a motor or something like this. And the user told me, he said, no, don't worry about those. Those are measurements that we make the operator log because we want him to go look at the equipment every day. And so I said, do me a favor, take this list. And I made them a list of all these manual inputs. I said, take this list and take it to the engineers that do the plant surveys. And you ask them if I should keep any of these data or not. And they came back with a list. And of course, somebody had taken a yellow marker, or multiple people had taken yellow markers. And every variable there had a yellow mark through it. And there were a bunch of variables on the bottom that I didn't even know about. The logical conclusion there is that when we were looking at the task to be done, we were looking at the task of what we were doing at the time, which was control automation of these big process units. We were not looking at a second task, which is the surveys, the material balances, the long-term scheduling of these operations, and they take a different data set. So that's really an important thing to remember, is that you have to get the right data set or you'll never solve the problem.
Okay. And what would you say to folks that say, we'll just add this stuff later?
People will say that. In fact, with software, people will say that even more, because they'll say we can add it later because software is easy to change. Well, I have a hint for you. Nobody that's ever said that's done software. Software is one of the most difficult things to change there possibly is, because there's no standards beside it. You can do anything you wish. You have this free format. Whatever you see, it isn't easy to change. There's, first of all, nothing's easy to change in the field, and software is particularly difficult, especially if it's going to change the instructions or the perception of the people using the system. So I predict that whatever data you have the first day is the only data you'll ever have. And if you work on that premise, then you're probably better off than assuming you can bring in what you needed.
Okay, great. So next rule, I guess this has to do with like the rate of implementation, but your expenditures, you're suggesting control your expenditures by your rate of implementation, not your goals. How's that relate?
Well, what I was really trying to say there is be really honest on what your goals are, because you get in the front end of a project and you'll have different people that are buying the system. Maybe they minimize the goals because they want to keep their price down. People are selling the system. Maybe they minimize the goals because they want to get the sale. After you start the work, though, the people that are using the system, they want to expand the scope to everything they ever wanted and never told anybody, because they were going to wait until they get a chance. And you get into this conflict. So what I was really saying there is, don't try to control the expenses of a project by your goals. The goals are the goals. If you have a finite set of resources, whether that be money, computers, etc., control your expenditures by the rate at which you implement those goals, but keep those goals fully in mind.
Okay, right. Okay, next up. Take the smallest scope you think will be successful, and then take the largest scope you can afford and add them together.
Well,
what do you mean by that?
That's really saying a similar thing, in that it's attempting to do it in a funny way, because of course people expect you to say take the smallest thing you can afford and the biggest thing and average them. No, I say you take the smallest thing and then the biggest thing you can afford and add them together. What I'm really saying there is you're going to use capacity far more than you expect. And I don't know where it's going to come from, and I don't know what it's going to cause. But of all of the problems in life caused by having too much capacity, they are minuscule compared to the cost of having too little.
Okay. Another interesting rule. Learning is like eating a big cookie. The bigger the bite, the more boundary there is to inspect and innovate.
I actually remember somebody saying that. Then they had a picture of a big old chocolate chip cookie. And the point they were making is, if you take a big bite out of that cookie, the boundary of that bite is bigger. And if you can visualize your project, they're similar in a way, in that the more you do, the more boundary there is. And so if you're doing of a certain scope and it's all contained, you have a certain boundary and you get some time to explore those boundaries. But then if you do a really large project, you got a very large boundary. And the other issue is that if you look at that cookie, if it's a big enough cookie, it never stops expanding.
Okay. Next rule. Unlike all other resources, data is different in that the more people that consume it, the more valuable it becomes.
That's an interesting phenomenon that we've discovered as we start communicating better, because people talk a lot about data as a resource, and it is a resource, but other resources, they're used to conserving. If energy is a resource, you conserve it. You try not to waste it. If materials are being used, you try not to waste them. But information is very different than that. The more people, the more eyeballs, the more use of that data, the more valuable it becomes, because the actual use of the data can create value that goes with it and then carries with it from then on. So data just increases in value the more people you express that to. If you take data, for example, and run a model for a digital twin, you now have the output of the digital twin that is an expansion of that data that maybe converts it into a form more easily used by others. So realistically, information is something that it needs to be used, whether it's used by people or used by algorithm, it needs to be used. And in the act of using it, you both increase its quality and you expand its value.
Okay, next rule. Value if monotonic with scale and always up. I'm sorry, did I even quote that right?
You did quote that right.
Okay,
And
what in the world is that? I do not get that. Is that even a sentence?
it's actually, well, you may have left some words out of it, but the actual theorem is that there's two parameters you're dealing with in a big project: scope and scale. In simple terms, think of scale as the number of points, the number of sensors, the number of tags. It's a relatively low level, but a hugely plentiful parameter. But now let's look at scope. Scope would be not so much the number of points, but the number of different places it came from. So scope increases out. And so if you initially had your project where you were in one plant, bringing in data for one plant, to increase the scope, you might then go to multiple plants. To increase scope again, you might go to the whole enterprise. To increase scope again, you might go to multiple enterprises of similar data, and you might actually go down in the number of points, but the scope is increasing. And what I'm saying is that throughout all of my career, what I've seen is the bigger the scope, the wider the scope, the more value the data can create. You still have to create the value, but the potential value is much higher if, for example, you're doing some application that has all of the plants within an enterprise. Your potential value is much higher than doing a particular thing in a particular plant.
Okay, and it goes beyond just within one organization, right? With the community system.
No, it's not just one organization. Data's data. Organizations and ownership and people and plants and enterprises, these are basically our artifacts of how we separate information. But information is information. So if you're looking at a smart city, for example, there's all sorts of different facilities and plants and industry, buildings, transportation. They're all in that city. So the community concept says that the data can expand to multiple owners as long as you track and maintain the data ownership and make sure that you're not becoming a leak between one owner and the other.
Okay, well, there's one left, and that is there are no solutions, only choices.
That's an interesting one. That actually was in a speech by a Republican strategist. Actually, I think it was a pre-Bush. It was a long time ago. And I don't know if he was talking about climate change or transportation fuels or pollution or whatever. But what he went through, and I can go through an example, for example, with power, is that you're always making choices. You don't really have a real solution. You're just making choices. And one of those examples would be, say, renewable energy. Now, everyone would say, well, if you put windmills and solar in, you're always decreasing the amount of greenhouse gases, and you're increasing our livability and all that. Well, if you know the power industry, what you find out is that if you put in solar or wind, these are non-dispatchable power resources. And so now the power company has to put in very fast-moving, dispatchable power resources to match these non-dispatchable resources.
I'm sorry, what's non-dispatchable mean?
You
lost
can't, a centralized person can't say, I want to run this many megawatts, because the wind blows and the sun comes out and you have no control over how much power
I
is
see.
generated.
I see what you mean. Yeah.
So what that does is, by now having to manage all this intermittent power, you will have to take your very efficient, what are called base loads, these units that run absolutely constant, and maybe you have to turn them down a little bit and use less efficient units to be able to handle the control part of it. The bottom line is that, yes, these are physics that you have to go through and make sure that you're not deteriorating a problem with your, quote, solution. But that was just a guideline to say, be aware of this. Look for not just what you think is the solution, look for what trade-offs you're actually making. Because almost invariably, you make trade-offs, you don't really solve problems completely.
Okay, great. Well, great. I think we've gone through all of the rules. And actually, one thing we didn't do, and I wish we had started with this, is the reason we even got into this is we did last time we spoke, we talked about the product history. Now we wanted to talk about the future. And you made an interesting point about trying to talk about the future. Can you explain that?
Well,
and why we actually talked about rules instead of talking about the future.
So there's lots of sayings about future, really hard to predict, particularly in the future. Those kind of things attributed to everybody from Niels Bohr to Yogi Berra. But the thing is true. Predicting in these businesses is really difficult. And I challenge anybody. You say, okay, I'd like to see where we're going for the next 10, 20 years. Go back 10 or 20 years. And tell me how much you would predict about what we're seeing today. Would you have predicted this move to the cloud, this ability to process down at the edge reliably? Would you have seen these new processors coming out that dwarf what we know of 10 years ago as a processor? There's more compute power now in your watch than we used to have in the computers we were doing this with. And so what I saw when I saw that is that I don't know that I can predict what will happen in 40 years. But what I can tell you are the rules that we have used and learned in the last 40 years that will pretty much guarantee a good a good result for the next 40 years. And that's really what I was trying to get to. If you stick by the rules, then what we're doing is going to be just good, solid engineering. We don't really need the breakthroughs. There are people that are going to make the breakthroughs without us. What we're supposed to do is learn how to use those breakthroughs and bring the kind of value and pleasantries that come from success.
Okay, well, I mean, speaking of predictions, I should just add, I can't resist adding that you've had some awfully good predictions over the years. And I just want to mention a few of them. I recall back in the days when Alta Vista was the biggest way to find things in the world, before Google was even in beta. In the lunchroom one day, you just mentioned, the future of the internet is search. And everybody's like, what, search? So you've been awfully good at doing some prognosticating of your own.
So did you want any predictions?
Yeah, sure. Can you make some predictions?
So I will predict a few things for you, because they're not really predictions. They're more observations of what's going on right now. One of them is that we seem to need some catchphrase in order to make progress. So over the last 10 years, we've had digital transformation, Industry 4.0, IoT, Y2K. Remember Y2K?
Yeah, right.
I remember the night that Y2K happened, and we, of course, were pretty sure nothing would happen, because fixing flaws in software from a time base are things that we've been doing for decades before that. And pretty soon, support lines of various companies started calling each other because nobody was busy and they wanted to talk to somebody. But anyway, one thing I do see is that one of these catchphrases that means absolutely nothing is IoT. Professor Porter made a good statement. He said that IoT is neither the internet nor is it things, and yet it's the Internet of Things. What it is, it's the catch-all that basically new kinds of sensors get thrown into. And I see a couple of these sensors, and I'll call them, let me call them waveform or two-dimensional sensors. These are things that measure more than just a point. These would be cameras with infrared lenses on them. These might be synchronous phasers that thoroughly inspect the waveform of a power line. These might be vibration sensors that look for movements that we can't see, but they have a real effect coming in the future. What really is going to change the world are when we really learn how to use these new sensors with the kind of software that's coming around parallel. And I'll just mention one article I read the other day, and that was McDonald's is putting cameras on their trash bins. And you say, well, why would they do that? Well, they have put artificial intelligence in them to tell what people are throwing away. And when people throw the wrong things away, the ability to recycle is not nearly as great. Or they put them in the wrong bin, or somebody comes and throws something in that doesn't belong there. And they actually said in the article that they were interpreting these camera images to count what people were throwing away and what quantity and what they were throwing away. And I suppose that will work. But what struck me on that is what a great new source of data. So if they're going to put cameras on there to keep people from throwing bicycles in the dumpsters, now I got more data I can record. I got the number of burger wrappers and the number of cartons and the number of plastic cups and the number of straws that people are throwing in the trash bins. And you think about that, now add that to that, all the other things that you could sense with cameras. And then on top of that, put in these new instruments called LiDARs, which are these lasers that spin around at 200 RPM and pick up everything movement within the perimeter of an autonomous vehicle. And by some estimates, these instruments will put on the order of 1 billion pieces of data an hour out for every autonomous vehicle. So these whole fleet of new waveform type of sensors, I think, are going to change the world. How they change it, I don't know. I'm an implementer. But I know that once we get the data out and we feed it to either artificial or human intelligence, somebody will figure out a way to use it.
Yeah.
And I should say the one other theorem, if you will, that was actually a paraphrase off of a statement that was by a professor that was talking on the subject of the data. He just kept saying it's all in the data. So you can ask if something's going to fail. You can ask if something's running properly. You can ask all these questions, and he would just say it's all in the data. The challenge is taking it out of the data. And the way to get it is, first of all, you have to capture it. And so, this is a good business for OSIsoft. We capture data. And all we do is we take it to the intelligence, whether human or artificial, and let them do their magic on it. And there's just more and more of it coming. It's going up. If anything, it's going up faster than Moore's Law.
Right. Okay. Well, thanks. Hey, Pat, now you actually wrote a paper that had a lot more detail on all of these rules. Is that something that's ever been published? Is that something I can put a link to, or is there something you'd be willing to share?
It's not published right now. It's an instruction. I call it the third flow. But it basically talks about information flow in industry. Okay. I will finish that at some point, and if there were requests for it, maybe that even forces me along a little bit. Okay,
right. Well, I'll hopefully we can look forward to that. But okay, thank you so much. We've been talking today to Dr. J. Patrick Kennedy. He's the founder and CEO of OSIsoft. So thank you so much, Pat.
Thank you, Nick.
Okay. Take care, everybody. Bye-bye.
Bye.